Hello everybody, we continue, and today I would like to start with last section of chapter 2 about complex numbers, and as usually this section, all sections are enumerated by the number of lecture. So today's 5th lecture, section 5.1, and roots. Now we talk about roots of a complex number. So nth root of a complex number. What is it? W. It means that we want to solve the equation z power n equals to w. So z, a solution, z is called nth root of w. And this video is wrong. The date is, what is it? No. So something wrong with the date, but other students saw in the video that said, and today is 16th, it's okay. I don't understand what's wrong. Ah, now it's okay. Okay. So, and let's try to understand how to solve this equation. So, write w in trigonometric form, model w times cosine argument of w plus I sine argument of w, or shorter, let's say like rho times cosine phi plus I sine phi. So this number is given, and we suppose w not equals to 0. Hence rho not equals to 0, and we can define also the argument. Otherwise we cannot define the argument of w. Now write z in a trigonometric form. So it means r times cosine psi plus I sine psi. And if we substitute it to our equation, we obtain, so substitute into the equation, and we obtain power n equals to rho cosine phi plus I sine phi. But we know the Moivre formula, which says that we can write it as cosine n psi plus I sine n psi equals to rho times cosine phi plus I sine phi. What we can deduce from this equation? First of all, modulo r power n should be equal to rho. Hence, r equals to nth root of rho. This is arithmetical root, so just standard recall rho is greater than 0. Hence, this is nth root in the sense of real numbers. Unique number. Uniquely defined number. R is positive, so we have R is positive. That is usual nth root. What's about arguments? We know that arguments are defined up to 2 pi k. So another conclusion is the following equality. It gives equality for the argument. Now let us think about which values of psi give us different numbers, different complex numbers z. We know that argument is defined up to 2 pi, integer multiples of 2 pi. So it means that, for example, k equals to 0 and k equals to n give us, in fact, the same complex number. So, give equal numbers z. Hence, how we can avoid counting equal numbers? We can choose only, let's say, 0, 1, so on, up to n minus 1. It gives different complex numbers. So, what it means? It means that we have there are n complex nth roots of complex number w not equals to 0. And they are given z equals to nth root of modulo w times cosine argument w plus 2k pi over n plus I sine argument w plus 2k pi over n, where just one value of argument is chosen. So this formula is not very good. I mean, the writing is not very good, since usually we understand argument, this writing argument w as an angle which is defined up to additive multiple of 2 pi. So in this sense, this is a little bit, how to say, overwriting, so too much of information. Usually we don't suppose that argument is defined uniquely, but here it is better to choose just one value of argument. Just one value of argument, and then I may add additionally possible values of k which give different numbers of z. That is formula. I mean, once again, this writing is a little bit conditional. So you should, when you write like that, you should mention that here argument is understood as a unique number. So you choose somehow uniquely one of infinitely many arguments of W. Okay. For example, nth roots. Let's write nth roots of unity. So it means we want to solve the equation. That is example, right? Example. Z power n equals to 1. If we write 1 as in trigonometric form, it will be like that. 1 times cosine 0 plus I sine 0. So one of possible choices of argument of 1 is 0. I mean, in general, argument 1 is 2k pi, where k is integer. And we choose one value. Argument 1 equals to 0. And here it is written. So then if we substitute, we obtain z equals to nth root of 1 in the real sense times cosine 0 plus 2k pi over n plus I sine 0 plus 2k pi over n. Where k varies from 0 to n minus 1. And these are different numbers. Shortly, we may forget about those stupid signs for nth root of 1 and so on, and to write just like that. We also may indicate by the index k that these are n different nth roots of the unity. And where they are, let me draw a picture. Let's choose n equals to 6 and write down on the Argand diagram. So 1, that is real, imaginary, and okay, let's indicate where they are. So k equals to 0. Maybe I'll write it here. Z0 is cosine 0 plus I sine 0, that is precisely 1. So this is Z naught. Next, k equals to 1, Z1 cosine 2 pi over 6 plus I sine 2 pi over 6, and that is cosine pi over 3 plus I sine pi over 3. So cosine pi over 3 is 1/2, and sine square root of 3 over 2. So it gives a point. Okay, let me draw a punctured circle of radius 1, minus 1, minus I, and if we take 1/2, then that is square root of 3 over 2I, so that is Z1. Next, k equals to 2, Z2 cosine 4 pi over 6 plus I sine 4 pi over 6, that is 2 pi over 3, and we have minus 1/2 plus I square root of 3 over 2. So symmetrically here Z3 k equals to Z2, sorry, k equals to 3, Z3 cosine, so we substitute k equals to 3, it gives 6 pi over 6 plus I sine 6 pi over 6, that is cosine pi is minus 1, sine pi is 0, minus 1, Z3 k equals to 4, Z4 cosine 8 pi over 6 plus I sine 8 pi over 6, that is 4 pi over 3, and gives same numbers but with minuses. So that is minus I square root of 3 over 2, Z4, and the last k equals to 5, Z5 cosine 10 pi over 6 plus I sine 10 pi over 6, that is 5 pi over 3, it gives 1/2 minus I square root of 3 over 2, that is here, Z5. So if we take k equals to 6, we have 12 pi over 6, that is 2 pi, and same as 0. And you see that where are all those points? They are placed, in fact, in as vertices of the right hexagon. And that is true in general. So nth root are vertices of the right polygon. So, okay. And now I would like also to mention one nice consequence of the Moivre formula. Of course, it could be mentioned in the previous section as well, since I gave the Moivre formula in the previous section, but that is not a problem, and also it's good to write down binomial formula. So let me recall once again the Moivre formula. That is cosine phi plus I sine phi power n equals to cosine n phi plus I sine phi. So, I mentioned during previous lecture that it can be used, for example, to write down cosine of 3 phi in terms of cosine and sine phi. And another consequence to write it down, it's okay, you can use it for n equals to 3. What is about others? So you need to be able to write down nth power of the sum of two numbers. And it can be done how? That is, of course, that is not about complex numbers, frankly speaking, right? But, okay, so binomial formula. What is binomial formula? A plus b power n equals to sum k from 0 to n and k binomial coefficients. Binomial coefficients a power k, b power n minus k. And binomial coefficients, how to compute them? Okay, there is formal formula. Binomial coefficient n factorial k factorial times n minus k factorial. Where what is factorial? Factorial n factorial is 1 times 2 times so on up to n. Also, we agree 0 factorial is 1 by definition. And this is not a good idea to compute binomial coefficients using that formula for large values of n and k. And so one can put them into so-called Pascal triangle. What is a Pascal triangle? In letters, it looks like that. I mean, better to say, not in letters, but in notations, right? So, we place binomial coefficients 1, 0, 1, 1 as a triangle like that. That is an infinite triangle. That is an infinite triangle. So you can continue up to infinity. And this triangle has a very nice property, namely, every number in the Pascal triangle is equal to the sum of numbers over 8. What means over 8? So, for example, over this number we have 2. Here, over this number we have 2. So, okay, over 5, 0, just 1. And so there are 2 numbers. So maybe it's better to indicate 2 numbers over 8. Of 2 numbers over 8. So how it looks like in letters? So it means that, and there is lemma, which we will prove now. Lemma. Main property of binomial coefficients. That is as follows. Okay, which letters to choose? Let me. Okay, I'll choose N, M plus N. Okay, let me put here M minus 1 and M equals to N plus 1 M. And that is valid for all M from 0 to N equals to from 1 to N, and N from 0, okay, let's say from 1 and so on, right? 1, 2, and so on. So proof. Proof is easy. Just write down by definition n factorial over m minus 1 factorial times n minus m minus 1 factorial plus n factorial over m factorial times n minus m factorial. Okay, so what is here? Here we have n minus m plus 1. Now look at m factorial and m minus 1 factorial. These are products of all natural numbers starting from 1 up to m minus 1 here and up to m in the second term. Hence, the first m minus 1 natural numbers are contained in both denominators. So, if we want to make it to add those fractions using common denominator, then the common denominator for first terms of products will be m factorial. And analogously, here we have n minus m plus 1 factorial, and here n minus m factorial, so common denominator should contain n minus m plus 1 factorial. So that is the common denominator of those two. So additional multipliers for the first fraction n factorial times, we should multiply by n. For the second term, for the second numerator, n factorial times n minus m plus 1. N minus m plus 1. Okay? Then, if we use distributive property, we have n factorial times n plus 1. And it gives n plus 1 factorial in the numerator. And here I'll rewrite it this one. And that is precisely binomial coefficient n plus 1. So we have proved the main property of binomial, or the binomial coefficients. Binomial coefficients. So now, let me indicate how it looks like in numbers. So 0, 0, we construct Pascal triangle. It's same Pascal triangle, right? Same Pascal triangle. These are equal triangles. And edges contain only units. So we put units everywhere. Maybe I'll shift slightly. Units on the edges. And then, so the first row contains only one number, second row 2 numbers, third row 3 numbers, and here we have just sum of those 2. It is 2. Then sums of those 2, 3, 3, and so on. So 4, 6, 4. And we continue. 5, 10, 10, 5, 6, 15, 20, 15, 6, 7, 21, 35, 35, 21, 7, and so on. We may continue up to infinity. And look, a plus b squared, just coefficients 1 to 1, a plus b cubed, 1, 3, 3, 1. And that is indeed the binomial formula, so how it was written. And now proof of the binomial formula. By induction. By induction. So, we should start induction n, of course, because k is just an index. N equals to 1. Start with n equals to 1. Let me write down what we need to prove. That is what we need to prove. I put everywhere n equals to 1. Now, okay, the left-hand side is just a plus b. Let's write the right-hand side. Here, we summarize terms for indices k equals to just 0 and 1. So we have 2 terms. k equals to 0. 1, 0, a power 0 is 1, b power 1, plus k equals to 1, 1, 1, a, and b power 0. And those numbers 1, 0, substitute 1 factorial, 0 factorial, 1 factorial. 1 factorial is 1, 0 factorial is 1 as well. So b plus. That's it. Now, if we proved for n equals to, let's say, m, so this is induction hypothesis, we just proved. And we want to prove it for n equals to m plus 1. That is what we want to prove. Induction hypothesis here. So we suppose it's true. Oh, sorry, here m everywhere, m plus 1, m plus 1 k, a power k, b power m plus 1 minus k. So that is the formula which we want to check. How? Just substitute. So, what I mean by substitution? What is the left-hand side? That is a plus b power m times a plus b. So we need to substitute the induction hypothesis and to multiply it by this sum. So I multiply by a firstly, k from 0 to m, k, a power k plus 1, b power m minus k. So I multiply by a and then by b. That is k from 0 to m, k, a power k, b power m plus 1 minus k. Okay, let's stop for a while. Okay, let's continue. So we continue our proof. Once again, what we did, we represent a plus b power m plus 1 as such a product. Then we substitute a plus b power m from the induction hypothesis and multiply firstly by a, here, and second term by b over there. Now, look, if you compare it with the result, with the desired result, then you see that the second term contains letters in precisely same powers as we want, right? But concerning the first term, this is not the case. How to avoid this situation? Let us denote in the first sum only k plus 1 equals to j. So it means k equals to j minus 1. Okay, what we have then? We continue. Maybe I'll write like a chain of equalities. The long chain of equalities. Just transformations. So we transform at the moment only the first sum. And transformation is using this substitution. So k plus 1 equals to j, or similarly k equals to j minus 1. K equals to j minus 1. So then how j varies now? K starts from 0, hence j starts from 1 up to m plus 1. So the first sum now will be j from 1 up to m plus 1. Then m k equals to j minus 1. J minus 1. A power j, b power m minus j minus 1. That is the first sum. The second sum we don't touch. K from 0 to m k, a power k, b power m plus 1 minus k. Now look, what is with the first sum? Imagine that we have, instead of j, we have just k. Here what we have? M minus k plus 1. So the same as here. So it means that if we return the same notation for the index of summation, so j, instead of j, we will write again k. Then we have the same expressions in powers of a and b. So we can unify both sums in one sum. But we have some problems, namely, now indices vary in different intervals. So in the first sum, the index starts from 1 and the last value of this index is m plus 1. In the second starts from 0, the last is m. So we proceed as follows. Maybe I'll use one more equation to replace again j by k, but simultaneously what I want to do, the common interval for both sums, common interval of indices, from 1 up to m. From 1 up to m, we have here and here as well. From 1 up to m. But from the first sum, we lose one term with j equals to m plus 1. So let me start with this term. So the first term, it's j equals to m plus 1. I will write it here, right? J equals to m plus 1. So we have m, j equals to m plus 1, m, a power j equals to m plus 1, m plus 1, b power j is m plus 1, no b. Okay, maybe I'll write b power 0 nevertheless. Then we have other terms, j from 1 up to m, and I return to k instead of j. From 1 up to m, m k minus 1, a power k, b power m plus 1 minus k. That is the first sum. For the second sum, again, I write separately k equals to 0. So we have m 0, a power 0, b power m plus 1. And then other terms, k from 1 up to m, m k, a power k, b power m plus 1 minus k equals to, so what are those coefficients m and m0? Let me write them. m and m0 are equal to 1. But also m plus 1, m plus 1, and m plus 1, 0 are also equal to 1, right? So I'll replace them by similar expressions. And what are expressions then? Okay. Okay. In the first term, instead of m, I'll write m plus 1, 0. Is another way to write down just 1. A power m plus, m plus 1. M plus 1, m plus 1 into that. It's also 1. A m plus 1, b 0. The third term. Here instead of m0, I'll write m plus 1, 0. A power 0, b power m plus 1. And other two sums, I'll collect all terms together and write it in one sum, k from 1 up to m. And we observe also that powers of a and b are the same, so we have distributive law, m k minus 1 plus m k, then a power k, b power m plus 1 minus k. Then we apply our lemma. No, here it was m. Instead of n we have m, instead of m we have k, right? So I will rewrite like that. M plus 1, 0, a power 0, b power m plus 1, plus sum k from 1 up to m. So these are equal, we add them by lemma. We have just m plus 1 k. And last term was the first. So, and the last step is to observe that this is indeed what is sum from k. K starts from 0 up to m plus 1. M plus 1 k, a power k, b power m plus 1 minus k. So look, k equals to 0, this term. Then k from 1 up to m, it's here. And lastly, k equals to m plus 1, this one. So now we have proved our formula. So the binomial formula, together with the Pascal triangle, can be used, for example, to write down, let me use once again, n equals to 6. Look at the Moivre formula, where n equals to 6, cosine phi plus I sine phi power 6 cosine 6 times phi plus I sine 6 times phi. And now I can rewrite the left hand side part using the binomial formula and Pascal triangle. So n equals to 6, it's here. N equals to 6. That is because just n1 is always n. Just look at this. N factorial, n minus 1 factorial. So just n remains. So, and then we can write cosine power 6 phi plus 6 cosine phi times I sine phi plus 15 cosine squared phi I squared sine squared phi plus 20 cosine cube phi I cube sine cube phi plus 15 cosine power 4 I power something wrong. Yeah, cosine power 5. Here cosine power 4. Cosine cube cube. Then cosine squared. I power 4 sine power 4 plus 6 times cosine phi I power 5 sine power 5 phi, and the last term plus 1 times I power 6 sine power 6 phi. And we may rewrite it. So terms real part cosine 6 phi minus 15 cosine power 4 phi sine squared phi plus 15 cosine squared phi sine power 4 phi and minus sine power 6 phi plus, now in G part, coefficient in I, 6 cosine power 5 phi sine phi minus 20 cosine cube phi sine cube phi and plus 6 cosine phi sine power 5 phi I. And if we compare, so that is transformation of the left hand side of the Moivre formula with the help of the binomial formula. And then if we compare the left hand side and the right hand side, then we deduce cosine 6 phi is cosine power 6 phi minus 15 cosine power 4 phi sine squared phi plus 15 cosine squared phi sine power 4 phi minus sine power 6 phi and sine 6 phi equals to 6 cosine power phi phi sine phi minus 20 cosine cube phi sine cube phi plus 6 cosine phi sine power 5 phi. And now let us substitute here phi equals to arc cosine x, or in other notations cosine minus 1x, right? Inverse function to cosine. Then what we have? We have cosine of 6 cosine minus 1x equals 2. So if we substitute cosine of cosine minus 1 is just x, x power 6 minus 15 x power 4. And what is sine squared? Sine squared is 1 minus cosine squared. So 1 minus x squared plus 15 x squared 1 minus x squared squared minus 1 minus x squared cubed. And yeah, so yeah. Analogously, I may proceed with 6 cosine minus 1x over sine x. So what is it? Divide by sine x, and we have 6x power 5 minus 20x cubed 1 minus x squared plus 6x 1 minus x squared. I took one sign, so right. So you see that those expressions are polynomials, and these are very important polynomials. They are called Chebyshev polynomials of the first and second kind. So cosine n cosine minus 1x is denoted by Tn of x. That is Chebyshev polynomial of the first kind. And sine n cosine minus 1x over sine x is a polynomial of degree n minus 1. That is Chebyshev polynomial of the second kind. They have a lot of applications. They're extremely for many problems. Okay, quite often they have normalizing, different normalizing. For example, here 1 over 2 power n minus 1 to make it monic polynomial, because here you see the leading coefficient is 1 plus 15 plus 15 plus 1, so gives 32, 2 power 5. And you can easily observe that if you substitute in general power n, you have same considerations, and always these are expressions for a polynomial. So in fact you may write also cosine n cosine minus 1x or x plus square root of x squared minus 1 power n plus x minus square root of x squared minus 1 power n and 1/2. So this expression is valid for x from minus 1 to 1, and here for other. X. Okay, we may include minus 1 and 1 without problems. So these are in fact polynomials, and how to see that they are polynomials, we need just to refer to the Moivre formula and binomial formula. Okay, that's all for the chapter 2. No questions. Very strange. Very strange. Okay. Now, chapter 3. We start chapter 3. And I erase everything here. So, chapter 3. Sequences and the limits. And section, as usually, first digit is just lecture number, 52. Quantifiers. Sequences. Notations. I'll start with quantifiers. Many times we wrote things like for all x in R, a formula, and let's say y in R as an example, right? X plus y equals to y plus x. And we may use quantifiers. So the first quantifier just to replace for all, right, A. And we may write that is the same. So the first quantifier for all, for any, it's also for any, for every, just for short writing. But that has logical, rigorous logical sense, but I don't want to go deeply inside mathematical logic here. So we'll use quantifiers first of all just for short writings, but of course we have logical sense. So, and negation for this, negation. So we want to write down something opposite. So here we wrote an axiom, right? Something, a proposition which is true. Proposition which is true, right? Now we want to understand what is negation of this proposition. So what means not valid? This proposition is not valid. It means that they exist x in var and y in R such that x plus y not equals to y plus x. Of course, yeah, and I'll write this with help of quantifiers. So that is precisely for they exist, right? They exist. There is. There is. And yeah, of course, that is true. True. That is wrong, right? So we have two propositions. One of them is negation of other. The first one is true, and the second is wrong. So that is about quantifiers. Now, sequences. What are sequences? Okay. A rigorous definition of a sequence is, this is just a map from the set of natural numbers to a given set. I don't want to use this rigorous definition, so a sequence of real numbers is the list of real numbers x1, x2, x3, x4, so on. So, once again, there is a rigorous definition. That is a map from natural numbers to real numbers. So, it put into a correspondence to 1 a number which is denoted by x1, to the number 2 a number which is denoted by x2, and so on. But that is a rigorous definition, and it's sufficient just to understand that a sequence is just a list of real numbers. And how to denote it? We use several notations. So full notation is like that. More briefly, just like that, right? So that is notation for a sequence. Of course, numbers need not to be different. So a sequence may contain the same number which is repeated infinitely many times. And there are several examples. So how to describe a sequence, how to put it, how to define it. Okay, several examples. Sometimes we may write just formal definition. Let's say xn equals to b1 q power n minus 1. N equals to 1 and 2 and so on, right? So we have sequence, members of that sequence, they are terms of the geometric progression. Geometric progression terms. Geometric progression terms. Another way just to describe, let's say xn is nth digit of decimal representation for pi. That is complete description of a sequence. What is known? That the sequence is never stabilizing. I mean, you cannot have the same digit from certain place up to infinity. Also, this sequence is not periodic, since pi is irrational. It was proved. And okay, so for that sequence we have x1 is 1, x2 is 4, and so on, right? And there is a question, and that is a kind of competition, mathematical competition, how many digits of this representation to find. And okay, I don't know about current records, of course more than million, but it's not an easy task to compute members of that sequence, and of course nobody can give a formula up to now for members of that digit. But nevertheless, the sequence is described completely. And one more example, Fibonacci sequence. F0 is 1, F1 is 1, and Fn equals to Fn minus 2 plus Fn minus 1. That is Fibonacci sequence. So we have 1, 1, 2, 3, 5, 8, 13, 21, and so on, right? That is the Fibonacci sequence. And that is also, so it means there is a recurrence relation. So these are main three ways to determine sequences: explicit formula, explicit description, and recurrence relation. And you see that sometimes, so for example here, Fibonacci sequence starts from 0, right? And if you put, let's say, xn equals to square root of n minus 2, then to have a real number, you should start with 2. So you need not to start just from n equals to 1. That is not so important. But you should have infinitely many terms nevertheless. Okay. And maybe what else I should mention here? Yeah, sometimes also we put brackets here as well, right? And also we may write like that, xn and is in n. That is also possible. Yeah. Of course, one can consider also sequences of complex numbers as well, right? Like that. But it is also possible, sequences of the complex numbers, but we'll not consider them since we don't plan to define limits for complex numbers in this chapter at least. Yeah, so I plan to define limits only for sequences of real numbers. Yeah. Okay, that's all for today.